Hey everybody, this is Larry. This is day 17 of the Leetcode Daily Challenge. Hit the like button, hit the subscribe button. Let me know what you think, and yeah, join the Discord channel. I've been kind of working on that to kind of make it interesting. Let's see what today's problem is. Surrounded region. Okay, well, let's wait for it to load. Is it having issues? Okay, let me refresh. Cool. Surrounding regions. Given a 2D board containing X and zeros, or the letter O, can capture all regions surrounded by X. A region is captured by flipping all zeros in or O's into X in a surrounding region. Okay. So basically, I shouldn't be on the border. Okay. So basically, we're just trying to do a variation of item finding or connected components. We're trying to find the zeros, and the key to these problems is just trying to figure out how to rephrase it in a way that you can program it, right? And in here, when you think about it as connected components, then immediately you could do depth first search or breadth first search. But the tricky part is separating out the ones that can touch the borders and the ones that cannot. So here, I think the idea is just do a depth first search when you see a zero, and then if you're able to reach outside, outside the box, and see something that's not X, then later on flip them all to X's. And then at the very end, we return, or we modify it in place, so we don't have to return anything. Okay, so that's probably the idea of what I'm going to do. Yeah, okay, let's get that started. For me, in Python, I mean, you could do this in various ways in different languages. I'm going to do it with depth first search, with recursion, and yeah, I mean, I think that's pretty much it. And I think I'm going to have some helpers to let me know if I need to flip the current things. Yeah, so, and once you get the algorithm, it becomes an implementation problem, which, with practice, you can figure out how it is that you'd like to express your algorithm. For me, in this case, I would like to put it into 3 states for each cell. So I would have maybe one cell for just untouched, or one state for untouched, one for in progress, and then another for finished. And then with that said, and then we could just maybe just make them into enums for like 0, 1, 2. And on an interview or something like that, you could talk about how you would talk, make them into actual enums. But then in the interest of time, we'll just do it this way. And then now we'll just do state as let's see. Okay, so then number of rows is equal to the length of the board. Number of columns is equal to the length of the first element. And I think it doesn't tell me the constraint, so it's one of those older problems. So let's just do if rows is equal to 0, we just return directly. And also if columns is equal to 0, just return. And then now we set it up so that we just start them with the untouched state times, let's see, columns for each row. So this will set up a rows by columns matrix that gives us the state of the thing. So then now we just have to process it one by one. Yeah, okay. And there are a couple of ways we can think about doing this. For me, I'm just going to put it into a current vector or something like that. But I'll explain it as I go. But let's go from X is in range of rows. So for each Y. So in item discovery or connected components and stuff like that, we just have to make sure we process each cell at least once. And in this case, we only process the ones that are the letter O. I keep on saying 0, but it is the letter O. So if xy is equal to O, then we have to check that the state is equal to untouched. So in this case, it cannot be finished. It cannot be in progress. It could be finished. So if this is the case, we just therefore search on xy. And here, let's just pass in a pending array. So that those are the things that are pending for us. So xy and pending. So, okay, actually, yeah. Put it here. Okay, that was a live code thing. But okay. Lucky that wasn't that embarrassing. Yeah, and then we'll do something afterwards, but yeah, we'll make this return a state, which is will return true. Or maybe we'll rename this to something even more so that it's more readable, which is can reach outside. And then we'll do if you can reach outside, let's pass for now, but we want to process states to change from O's to X. And then else is fine, we just have to just regularly process states. And I'll explain that when we get back to this. But yeah, can we reach outside from this place? So the way that I like to set it up is that, okay, if, what is our base case? So there are a couple of base cases we can consider, but let's set up the dx/dy. The way that I like to set it up is directions is equal to an array of just all the different deltas that you can go. And there's 4 different directions because we're only going up, down, left, right. And then now, just for dx/dy in directions, we want to go in all 4, which is if we have, and we only want to go to those directions if they are they're zeros or O's. So so let's say next, I just call it next x is equal to dx plus x, and next y is equal to dy plus y. So let's say if so if next x is less than 0, meaning it reaches outside on the 0 side, or next x is greater than the number of rows or greater than equal to because it's 0 index, or next y is less than 0, or next y is greater than columns, then we can reach outside. So let's put that in a variable, can reach is equal to false, and then here we would set it to can reach is equal to true. Otherwise that means and then we continue. Otherwise, then we look at the cell. If the cell is an O, then we want to go recursively, and only if it's not processed yet. Otherwise, that would be pretty not great. So state is, I forgot. So this is if this is 0, or the letter O. If the state is equal to 0, meaning that it is untouched, then we actually go can reach is equal to outside of next x, next y, pending. And we haven't done anything about the pending part, but at the very end we just return can reach, and that's pretty much it. Yeah. And here we want to add this cell to pending, so that's fine. And that should pretty much be it. We have to change the state to in progress, which is 1 as we look up this table. The enum for next. Maybe I could have just used a variable, but a constant. But yeah, but that's it for the recursion. So now we have to change the state from 0 to 6. So we can reach outside. Then we want to go through pending, and then let's go pending x, pending y, in pending. For each item in pending, we want to change it to what do we call it? Oops, to x, right? Is it capital X? Yep, I guess. And then in the default case, we want to change all the pendings anyway. So now that we're done, we do this again, but now we are changing the state to 2 for being finished. And then at the very end, that's pretty much it. Now we will process everything once, and let's give it some test cases for fun. Okay. Yeah, let's just run this for now first. I don't know if that's good. It doesn't. Oh, show diff maybe. Okay, so it does. So this is not good, but Oh, actually, I just got the logic backwards. That's all. Basically, you want to make it so that if you can reach outside, or if you cannot reach outside, you do this. So that's pretty much the only thing I have to change. I said it in English correctly, maybe, but the code is not okay. Okay, yeah. So now this is good. I think so. Yeah. Now I would say let's test a few more cases. Let's and this is kind of hard to visualize, but let's just pretend, and then this should connect everything outside. So then now nothing gets updated. If I get the, it doesn't tell me if I'm getting the wrong answer, right? Okay, but I feel like it used to tell you do the comparison. But yeah, so now because we have these if statements, I think we should be okay with the empty cases. But let's try the one case where it's an O, and then maybe just an X, and then maybe one more. Just giving it some love. Okay, so that looks okay. Let's submit. We'll see. Cool, accepted on the first go. Always good to hear. Yeah, so what is the complexity of this, right? So the complexity is that we look at each cell a couple of times for the constant number of times, right? Because we call it once for each cell. Here, for each cell, we put in pending once, and for each item in pending, we look at it twice at most. So that means we look at each cell about 4 or 5 times at most. So that's constant times each cell, and there are a linear number of cells, so it is going to be linear time, which is all of rows times columns, linear in the size of the input, that is. And space, here we do allocate extra space on a stack. I don't know that you can do better than that, because even with breadth first search or something like that, you probably have to keep track of the numbers that the zeros that are in the O's that are inside before you flip them, because you have to search to see if you could get outside. So yeah, so this is also linear in terms of space, because for me, Well, one is that the stack space could just be just go through every cell, roughly speaking, and pending could also be every cell, and also state. So actually, they're definitely linear time, linear space, and in this case, linear is represented in terms of the input size, which is rows times columns. So yeah, so this is pretty straightforward for competitive programming. This is a sort of a flood fill type algorithm, island finding, and all that stuff. So it comes up all the time. Definitely practice it. And recursion, breadth first search, both useful techniques that you get to practice here. So that's good. In terms for interviews, again, for interviews, these are pretty much very basic thing that you might that yeah, this may lead to a trickier problem, or like this is the first part of a trickier problem. So definitely practice it and be familiar with it. Be very yeah, be very comfortable with this kind of problem. Anyway, that's all I have for today. Thanks for watching. Hit the like button, hit the subscribe button, and join the Discord channel for hanging out. And I will see y'all tomorrow. Bye bye.